everyone, welcome to the High Energy Seminar. And today our first speaker is Dr. Daniel Castro, and he is currently a astrophysicist at the CFA for almost a year now.
Yeah.
And he got his education from Atlantic College, the University of Edinburgh, and the University of Simon Bolivar. And he did during his PhD, he was a pre-doc at the Center for Astrophysics working with Pat Slam. And after he got his PhD, he has been postdocs at MIT and Goddard. He has been working very closely with the Fermi Lab team on mission monitoring, data analysis, and science. Today he's going to talk to us about the monster next door.
Thank you, Yuan Juan. And thank you all for coming on a snowy, slightly wet day. So yes, as Yuan Juan mentioned, aside from being here at the CFA, I'm also a member of the Fermi Lab collaboration, which is sometimes a curse and sometimes a blessing. But yeah, I'm going to be focusing, I do quite a bit of work on X-ray observations of supernova remnants and pulsar wind nebula, but today I'm going to be talking a little bit about Fermi Lab observations. Since we don't get to hear about those all that often. And in this case, it's specifically about N132D, a supernova remnant in the Large Magellanic Cloud. So roughly an outline based in questions. Why should you care about the connection between supernova remnants and cosmic rays? This is always my motivation part of the talk, where I try and convince people that this is important stuff. Secondly, what evidence is there that supernova remnants indeed accelerate cosmic rays? And finally, going into what we've learned by studying these supernova remnants specifically. So starting with why you should care about it. All right, so there's several different reasons this list can be longer or shorter, depending on your personal preferences. The origin of cosmic rays is always a puzzle, and supernova remnants are suspected of being the main source of galactic cosmic rays. For example, the gamma ray background, as we see in the sky, this is a Fermi-Lat map of the entire sky in galactic coordinates, and you can see really bright emission from the plane. This is diffuse emission dotted with some point source emission, and most of the diffuse emission is expected to be cosmic ray protons interacting with the material in the plane. So all the gas is interacting with the sea of cosmic rays that is everywhere. So in order to understand any given point source of your interest, you really need to understand what that cosmic ray population is doing, where they're produced, how they diffuse away from those acceleration regions, etc. Another reason why you would care about supernova remnants and cosmic rays is because supernova remnants are this nearby resolved objects with really strong shocks that appear to be accelerating particles fairly efficiently. And they're one of the few examples that we have of efficient particle acceleration nearby to us that we can resolve. All right, so particle acceleration seems to be ubiquitous across the universe. There are many different systems that accelerate particles to relativistic energies. And then supernova remnants are a great lab to study that process. And in this case, I'm just showing you an example of a different type of shock accelerating particles. These are the shocks from propagating away from a star-forming region, NGC 3576, and these shocks are the result of the massive star winds that make up that star-forming region. Also, I mean, more specifically, of course, if you care about supernova remnants and basically what the progenitor systems are like, what the characteristics of the medium around a supernova explosion before it blows up, how the shocks evolve with time, the thermal plasmas that they leave behind. To understand just the energetics, you need to understand cosmic ray acceleration at the shocks. What systems are more efficient at accelerating cosmic rays? What magnetic field distributions and configurations are more efficient and less efficient at accelerating cosmic rays, in order to really build a complete picture of what your supernova remnant is doing. And finally, as we've heard in recent weeks here, in talks by Christoph Fromer and Volker Springel, cosmic ray feedback has, in the last 10 years, really been brought to the foreground in terms of understanding how galaxies evolve, understanding how large scale structural forms. The cosmic rays are very good at coupling to material at long distances, for example. So they're expected to be one of the main culprits behind launching galactic winds out of the galaxy, sort of launching large amounts of gas out of galaxies. So overall, this is important. Is an important connection to understand how cosmic rays are accelerated, and that's what we consider in supernova remnants, is because they're nearby, and we can there's a bunch of stuff to be learned from them. Right. So what evidence have we gathered up to now that supernova remnants actually accelerate cosmic rays? Right. So there's several different pieces of evidence. One of them is, if you study the shock structure from a supernova remnant, you can get indirectly information about the efficiency of particle acceleration at the shock. This is basically by looking at where the forward shock is in comparison to the contact discontinuity and the reverse shocks in the supernova remnant. And this is slightly model dependent, but overall, our observations in X-rays seem to suggest that the shock structures that we observe indeed show efficient particle acceleration. Secondly, also by using X-ray observations, there's non-thermal X-ray emission. So non-thermal X-ray emission, just by the fact that we observe it, and on the top right we have a nice Chandra picture of SN1006. In blue, most of the blue stuff that you see is really hard emission, mostly expected to be synchrotron emission from relativistic electrons interacting with the local magnetic field. So those relativistic electrons are, we understand them as being accelerated up to energies of TeV. So that already stands as a piece of evidence that these shocks are very efficient at accelerating particles to TeV energies. However, we know that most of the cosmic rays that are observed are actually protons. So, at Earth, about 99% of the cosmic rays that we detect are protons or heavier ions, not electrons. Electrons only make up to about 1% of the cosmic rays that we observe. So the question is always, how do we observe accelerated cosmic rays, protons, in these systems? Magnetic field amplification, which is also observed by looking at synchrotron emission in the X-rays from these particles. The way we understand magnetic field amplification in shocks is that your cosmic ray ions are interacting with the local magnetic field, and the magnetic field is itself the one that accelerates the particles, but it accelerates them by dispersing them. They disperse off turbulence and the magnetic field ahead of the shock and behind the shock, so that makes the protons or ions cross the shock several times. So basically, it becomes a perturbation to the magnetic field that is creating the cosmic ray protons become perturbations to the magnetic field, which in itself those perturbations are the ones that are accelerating your cosmic rays. So it's a very non-linear system. But the fact that we see magnetic field amplification at these shocks seems to suggest that cosmic ray protons are indeed being accelerated efficiently at the shocks. And then finally, the final piece of evidence that we've gathered up to now is gamma ray emission coming from supernova remnants. So on the left, I'm showing you 4 pictures of supernova remnants in the X-rays. They're all focused on the synchrotron emission from those remnants. And on the right, you see TeV observations done with ground-based Cherenkov telescopes of the very same supernova remnants. And you can see that the morphologies are very similar. Obviously, the resolution of the TeV telescopes is not as good as the one of the X-ray telescopes, but nonetheless, we can see that it follows basically the same morphology. So we can tell that some of the emission that we see from relativistic electrons on the left correlates well with emission detected in the TeV band. So we expect that to be emission from relativistic particles in the TeV band. However, there's always the debate as to whether what you're observing in the TeV band is leptonic in origin, so basically from relativistic electrons, or hadronic, so some type of emission from relativistic protons, which are really the ones that we want to see, right? So what have we learned by looking at supernova remnant N132D? Right, so let's continue on the same path that I was following just now. So we have these observations in the TeV band. So it doesn't show up so well here, but everything below 1 MeV in the non-thermal emission from a supernova remnant is dominated by the relativistic electrons interacting with the magnetic field. So synchrotron emission is dominant here. The black line is showing you thermal emission from the supernova remnant. So that's a combination of ion line emission with electron Bremsstrahlung. To higher energies above 1 MeV, we have 3 competing mechanisms of emission from a distribution of particles, of relativistic particles inside a supernova remnant. We've got non-thermal Bremsstrahlung from those relativistic electrons interacting with the ambient medium. We have inverse Compton emission, again, from the relativistic electrons interacting with the local CMB photon field and upscattering those photons up to gamma ray emitting energies. And then pion decay, which is the only hadronic channel of emission of gamma rays. So these are basically a relativistic proton hits an ambient proton. They both become, they combine to become a neutral pion, and that pion subsequently decays into 2 gamma rays, which will be always at energies above 60 MeV. So that's why it rises so quickly around 70 MeV, and then it will follow roughly the distribution of the underlying proton, relativistic protons, which are the ones doing the interaction. All right, so as you can see, TeV observations, which are 10 to the 6 MeV and above, are all really catching the cutoff of these curves. So it's actually really difficult to use those observations to tell apart whether what we're looking at is pion decay or inverse Compton, for example. So to know whether what you're seeing is from the protons or the electrons. And that's where Fermi came in about 10 years ago, opening this window where we seem to have a much larger difference in what we expect from the emission mechanisms from electrons and protons. All right, so the ones that I showed you in the slide before, let's go back to this one. The ones here are all detected in the TeV band. They're all dynamically young, powerful shocks. So basically they're either very young in age, or they've been propagating through very low density mediums. And the shocks are moving very, very, very fast, right? So when Fermi was launched, we expected to detect the same remnants also in the GeV band. And indeed, we detected several of them. As a matter of fact, we detect many of them that are like that. But and these three are three that were in the slide right before that are also detected in TeVs. But the majority of the supernova remnants detected with the Fermi-LAT are actually not young. So they're dynamically old. They've been they're interacting with very dense material. Most of them are suspected to be core collapse supernova from very massive stars that haven't that didn't migrate very far from whatever molecular cloud they were created in. And many of these detections, by the way, I should mention, have been reported by people who have come through the CFA, people like Katie Okato, who was a pre-doc here and is now at Ohio State University, Tim Joubert, who was here for a while and then he moved on to the Air Force, go figure. But nonetheless, I just want to say that there's a great majority of the supernova remnants detected with the Fermi-LAT are actually of this type on the right. All right. And indeed, interestingly, those supernova remnants are the first ones that we were, the old slow shocks interacting with dense material, were the first ones that we using spectroscopy were able to really tell that they were pion decay emission was what was being detected in that direction. All right, so in this case, IC443 and W44 are two supernova remnants that are interacting with a lot of dense material. The shocks are moving very slowly. And their gamma ray spectra show a rapid rise at the lower energy of the Fermi-LAT detection band. So this is about 100 MeV. As I said, they rise very quickly, around 70 MeV. And this blue curve is the pion decay model. And if you compare it to a possible Bremsstrahlung model, it doesn't seem to fit. And if you compare it to an inverse Compton fit, it fits even less well. And that's the same thing for IC443. So IC443 and W44 reported in 2013 were the first two that we definitely could tell that there were pion decay emission coming from them. So relativistic protons interacting with the ambient medium, which is very exciting. Now, why are these supernova remnants so bright in the GeV band? Well, it turns out that if you think about it, they're interacting with a lot of dense material, and since pion decay depends heavily on the density of the target, right? Because you've got all these cosmic rays that need an ambient proton to collide with, then whatever has a dense target next to it, you would expect to have some pion decay emission coming from it. Right, so fantastic. We found definitely proof that cosmic rays, cosmic ray ions are accelerated in supernova remnants. This is all well. This is we don't need to search for any more evidence of this. However, it turns out that motivated by our not understanding that these really, really slow shocks could produce such a large population of cosmic ray protons, people have looked more into this type of objects, and they've eventually come up with a model that shows that, well, that claims that these are not the result of freshly accelerated cosmic rays. So it turns out that these shocks, which are very slow, they've actually gone radiative, are very good at compressing material on magnetic fields. And what seems to be happening is that they're compressing the pre-existing cosmic ray C, which is available to them, to such a degree that basically what you're seeing is reaccelerated cosmic rays that were already there. Okay, and the reason that they're bright in the gamma rays is because, again, they're interacting with very dense material. So N132D, which is the one that I wanted to talk to you about today, is this beautiful supernova remnant that we see in the Large Magellan Cloud. There's a pretty Chandra picture over there where the red is the lower energy stuff and blue is the higher, harder X-rays. Its morphology is you see there is also matched by its radio emission. It seems to be analogous somewhat to Cas-A, so it's oxygen-rich supernova remnant expected to be the result of the core collapse of a very massive star. From the X-rays, just doing the sort of our most standard analysis, which is set of analysis of the emission that we observe, we can derive parameters from the system. Also, you can derive a density from the region. So it seems to be a little bit denser towards the south. That's why it seems brighter in the south. And that stuff seems to be 2 to 3 parts per centimeter cubed. If you apply a set of analysis, the explosion energy that you get is very, very high. So supernova explosions are expected to be, the canonical values are around 10 to the 51 ergs. This one suggests that it's somewhere between 2 and 11 times 10 to the 51 ergs, which is very energetic. And surprisingly, it's the age that we get for it is actually quite large. It doesn't seem to be all that young. And this supernova remnant is also detected at TeV energies with Hess. Right, so where do we place this in sort of terms of population? So how does it compare to, you know, other supernova remnants? Well, in the radio band, it's only second to Cas-A in terms of luminosity. In X-rays, it seems to be the brightest X-ray, the most luminous X-ray supernova remnant observed. I think Paul Plashinsky pointed out to me that there's one in a galaxy just outside the local group, which might be more luminous than this one in X-rays. But in terms of the local group, this seems to stand as the brightest one, and it seems to be an interesting question as to where do we place it in gamma rays, and what does that tell us about the system. In this list, I have a mixture of sort of young and powerful and fast shock supernova remnants, and then some supernova remnants that seem to be a lot less powerful, where the shocks are moving a lot less fast. And the reason why I place them there, you can see that their radio emission is actually not all that bright, and their X-ray emission is actually not all that bright, but their gamma ray emission is fairly high for the reasons that I outlined before. All right, so that's on the left. You have a count map of the Large Magellanic Cloud done with the Fermi-LAT. This is in the 2 to 200 GeV band. So it seems to be composed mostly of diffuse emission with some possible point sources inside of it. And those point sources were studied recently by Ackerman et al. 2016. And they seem to coincide with sort of the one marked as P1 is a very bright pulsar, the only pulsar detected with the Fermi-LAT from the LMC. P2 is a very, very bright pulsar wind nebula, analogous to the Crab in our own galaxy. P3 is a gamma ray binary, which is already a very exotic object. There are not many of them. And then P4 is suggested to be a counterpart of N132D, which we can all believe since it's also detected at TeV energies. Just want to point out that these four are very, very exotic, very, very powerful sources. And even though if selection effects tell you that they will have to be very powerful to be detected here, since the LMC is 50 kiloparsecs away. Nonetheless, it stands as an interesting little nugget of information. Now, if we concentrate on that white box sort of around N132D, so the green point, the green contours that you almost see there are the actual contours from the Chandra emission, and the data itself is a test statistic map, which is basically a significance map around this object, indicating that that it's detected to above 5 sigma in the gamma ray data. So its spectrum looks a little bit like this. This is not probably all that interesting unless we put it into context. But if you calculate the luminosity in gamma rays in the 0.1 to 100 GeV band, then it stands only second to W49b. And W49b is a supernova remnant that we know is very powerful in our own galaxy, and is also interacting with very dense material. So that's where it places it. Now, what does Chandra tell us about this stuff? The thermal emission from N132D is very interesting, but that's not really the topic that I'm looking into here. I'm concentrating on the non-thermal emission from the supernova remnant. And there's no way to really rule it out or rule it in, that there is actually non-thermal X-ray emission from N132D. Even a recent NuSTAR observation of it is inconclusive in that topic. So what I've done is I've used the thermal emission to place an upper limit on how bright could a non-thermal emission component be buried under there. All right, and this is what the broadband emission from the broadband spectrum from N132D looks like. So we've got some radio points down there at the bottom. This yellow line that you see here is the upper limit that I place on the non-thermal emission from N132D. The blue points are the ones that we extracted using Fermi-LAT, and then the green points are the TeV detection. There's a couple of broadband models to the emission, both non-thermal only, applied to this supernova remnant, and as you can tell, it's basically impossible from the data that you have to tell them apart, right? Nonetheless, I want you to take two things away from this plot, or from this slide. Both leptonic and hadronic fit, but both require an energy in cosmic rays that is above 10 to the 51 ergs. Now that's a really large number, since the canonical value for the explosion, for the kinetic energy from the explosion being placed into the material as it is ejected out, is 10 to the 51 ergs. Okay? So that means this is either an extremely, extremely energetic event, the explosion itself, or that it's extremely efficient at placing all its energy in cosmic rays. And from the thermal plasma that we see, we know that not all the energy is going into cosmic rays. So this thing must have been a very, very large explosion. And then secondly, I want you to take away that even though the leptonic model fits, it requires an electron to proton ratio of 0.1. Which is a very high number. It's basically saying that 10% of the cosmic rays produced at the shock are electrons, which is not what we expect. We expect it to be 10 times smaller than that. And also that the density needs to be below 1 part per cubic centimeter, which does not seem to be the case. And I'll show you, if we place it on a map, this is an infrared image with IRAC at 7.9 microns, which shows you basically where the molecular hydrogen in this region is. You can see that the supernova remnant seems to be sort of starting to interact with what was probably the same cloud where the progenitor was created. And the densities from these clouds range from, but they're all above 100 parts per cc. So could it be reacceleration? Well, it's a possibility. I'm here placing the spectrum from W44, one of the supernova remnants that I showed you before that are believed to be a reacceleration of cosmic rays. And that one required a density of 200 parts per cc at a distance of 3 kiloparsecs roughly. If we actually place that W44 supernova remnant in the LMC, then this is what it would look like. And now you can really compare the two spectra, and you can tell that the spectrum from N132D doesn't seem to be compatible with that of W44. So I'm not saying that this rules it out, but it definitely makes a compelling case against it. So I personally don't think that this is the result of a reacceleration. And if you look at them, if you compare them, it sort of makes sense that it's not the same kind of system. N132 on the right, and on the left you have in blue X-rays coming from W44 and some additional infrared and optical emission. But if you take the infrared and optical emission, that's what W44 looks like. It's brightened in the center, the shocks don't seem to be all that bright on the outskirts, and it doesn't look anything like what N132D looks like. And I'm going to leave it there. These are my collaborators in this and other works related to Fermi-Lat observations. And if you're curious about the Fermi-Lat results or anything like that, you're always welcome to come to my office and chat with me. Thank you. Sure.
You had these pion decay models on the spectrum.
Yep.
Can you say something more about how is that calculated?
Right. So these are particularly simple models. They're single zone models where you basically model the distribution of particles as being a power law in momentum in momentum distribution with an exponential cutoff that is basically a result of what your acceleration process would be like. So basically the cutoff is the cutoff here, which is related to the cutoff in the underlying proton distribution, is basically put in by hand. But the amount of energy in cosmic rays is what we sort of gauge as a parameter. Grant?
Dan, if you show the Chandra contours on the IRAC map of the cloud, the morphology of the remnant, it looks like a bubble's bursting just at the edge of the cloud when the cloud ends. Is that exactly what's happening?
It's possible. I think that's partly the story we want to tell. So it seems that it's interacting with the dense material towards the south, and that it's bursting out on the top into a lower density medium. So yeah.
What's the physical size of the remnant from end to end?
The physical size is, hold on, I've got. Should know this off by heart. So it's 50 arc seconds.
So that's like.
Sorry. Jan will come up with it in a second. 100 parsecs. Pat. Thank you, Jan. That seems large. Okay.
But what I was going to say is that with regard to the high energy content, I wanted to point out that energy is degenerate with the density of the ion calculation. So if the ambient density or the interactive density is much higher than you anticipated, then that energy comes down.
Correct. Yeah, that's definitely true. So the pion decay, the normalization of the pion decay component depends basically on two values: on your density of cosmic rays and on your density of ambient material. Right? So if you pump up the density of ambient material, then you can lower the amount of cosmic rays that you have. However, there is a limit at which you can pump up that density because in these models, you can have different models where you have escaping cosmic rays that actually diffuse away from the shock and interact with the cloud far away. But if you're using a model like the one I'm using, you're actually presupposing that the cosmic rays are interacting with the material that is just being shocked, right? And the shock wouldn't be that bright in X-rays if it was 100 parts per cc.
One more question.
Sure.
So much of this is powered by the proton-proton interactions. Do you think the densities that were derived, like few particles per centimeter, is that good enough for these interactions?
Yes, definitely. Yeah. I mean, the pion decay model here, it's definitely simulating exactly that. So the cross sections would work out to emit that much gamma rays from pion decay emission if you have those two densities being as we modeled them. Yeah.
Nice talk. Just a question about the discrepancy. We're talking about the energy in cosmic rays. So in the first part, you said that the kinetic energy is of the order between 2 and 11 10 to 51 Hz, which is much larger than for typical WC. But then you said that the energy cosmic rays is surprising of the order of 10 to 51, which is about 10% of the energy. So what is surprising is the absolute value, right? Not the factor.
No, you're right. So basically, both are surprising. However,
But not the fact that 10%.
no, not the fact that 10%.
Because if you have more kinetic energy, you must have more energy cosmic rays. So
Definitely, that's exactly right. It's not surprising that your set of analysis is telling you that this is a super energetic explosion. You're completely correct, because from the cosmic rays, we're finding the same. So the numbers that you find from the cosmic rays are basically the same. You can say that, well, if it's really 10 to the 51 ergs in cosmic ray protons in your system, then if you have 40% of your total energy being placed into cosmic rays, then you have somewhere between 2 and 3 times 10 to the 51 ergs. If you're saying that 10% of your energy is going to cosmic rays, then you have 10 to the 52 ergs. So you're right. They coincide. However, we never trust the results of a set of analysis done, at least not at first. So we're not always confident on those results.
how did you get the number of this percentage? Just
This one?
Yeah, how did you get the number? Just fit in the profile with the...
So in this case, this set of analysis is not actually mine. This is from Jack Hughes in 1997. But they get it from, basically, you have a density and you have a temperature. Even though the temperatures from the electrons, you can sort of derive a proton temperature from that, which can be connected to the velocity of the shock. And you have a size. So from those three values, you can derive the H, the energy of the explosion.
Let's move on to the second topic, same thing. Our second speaker is Dr. Atish Kamble, and he's a current postdoc at Supernovae. He's
Talk now. Should be good.
Hello? This is probably better. And these are also not supernova remnants of the kind of objects that Daniel talked about. These are young supernovae. So I'm talking about the time scale of 1 day to 1 year after the star explodes. So this is a brief picture about the morphology of supernovae, what happens. There is a star, a very massive, more than 20 solar mass star, which sits there for a million years or so and drives very powerful winds, which modifies the surrounding density medium around it. I've tried to bring it to the scale, but it's not quite there. But the vicinity of the stars is dense because of its winds, and there may be eruptions and other things that happen. But when the star explodes, its outer envelope is ejected, it's very high temperature material, it's radioactive, and it shines brightly in the optical. So that's how we discover supernovae. At the same time, there is a forward shock that goes and sweeps into the surrounding medium. It's moving very fast, of the order of like 10% the speed of light. And the material that is shocked, which sits right behind it, is at very high temperatures of the order of billion kelvins. Now, if you throw in a little bit of magnetic field, it starts to shine in synchrotron, and that's how we see supernovae in radio. At the same time, there is another shock that develops, and it sweeps back into the ejecta, which is called the reverse shock. It sweeps into dense ejecta, so it shines brightly in X-rays, and it has temperatures of the order of million to tens of millions of kelvins. So that's about brief supernova morphology. And then this is the well-known binary tree of supernova classification from its spectra. You ask questions like, is there hydrogen or no hydrogen? Then you get type 1, type 2, and various different types depending on what elements sit there in the spectrum. This is a pictorial description of the same thing. You have stars of different types and different layers sitting on them, which represent different types of supernovae. So if you have hydrogen, helium, everything, you get supernovae, which are type 2. And if the envelope is removed, like if you don't have any hydrogen left or helium left, what you get is type 1b or type 1c supernovae. Supernovae also differ in their evolution in the optical light curve, and there's a huge difference of the order of magnitude in their brightness as you go from one supernova type to another. Type 1As are the brightest, about minus 19.5 magnitude, and type 2Ps are some of the least bright supernovae. Now let's move back to the spectrum of supernovae. So what is shown here is the brightness on the y-axis and frequency on the x. So the bright peak that you see here is what you see in the optical. It's a broadband optical emission. That's how you discover supernovae. But underlies another very broadband emission, which is the synchrotron emission. It goes all the way from radio to X-rays. And so these are the typical bands. The broadband emission is powered by the synchrotron emission, and the optical is basically nickel-56 radioactive. So that's why this shows why it is important to observe supernovae in different wavebands, because you get different information by different observation. Now, I like to imagine supernovae or the radio supernovae as very bright, very big fireballs of synchrotron. And here is one nice way of putting them in perspective. So what is plotted here is the luminosity, the radio spectral luminosity on the y-axis. And on the x-axis, you have time when the radio spectrum peaks at a given frequency band, let's say 5 gigahertz. Now I can plot different types of supernovae here. So different data point corresponds to different type of supernova. So this is type 2P, then 2N, and various different types. You'll see that different types of supernovae start to cluster at different locations. This is, for example, type 1B and 1C supernovae. They have very broad distribution in y-axis. These are type 2P, type 2B supernovae, which are also explosions of very giant stars of the order of 500 solar radii. And now, because the supernova shock wave is an efficient way of converting kinetic energy into the random energy or the radiation, The only way the supernova can get bright is if you provide more electrons to convert that energy into radiation. So I can draw lines of different velocities here on this plot. So you go from 10,000 kilometer per second, 30,000, 100,000. You can keep going like that. What you meet is the relativistic cousins of supernovae here, which are called the gamma ray bursts. In between the normal supernovae and gamma ray bursts, you will find objects which we tend to call as engine-driven supernovae. And there are few of them. These supernovae, they do not necessarily have any gamma ray counterpart. They were discovered in optical, but they have shock velocities which are extremely fast, like of the order of 50% or even higher than that, the speed of light. Now, on the other hand, if you keep going down to the lower velocities, there are still a lot of supernovae sitting there. Are they moving very slowly? That's not true, because we know from their spectral lines that they are actually moving at several thousands of kilometers per second. What's happening there is that their emission is absorbed by their own material sitting out there. So the radio emission from these supernovae are absorbed by their winds by the process called free absorption. So these are extremely big stars that have exploded, and their emission is already getting absorbed in their own wind. So that much we understand from here. Now, we have about 12 minutes left. So I'm going to skip the first part, and I'm going to move on to the cosmic ray acceleration. So I'm going to move to these other extreme of supernovae which explode in extremely dense environments and which appear to be moving slow. So the supernova shock waves drive electrons to very high energies. They should naturally drive protons to very high energies too, just as Daniel was saying before me. So what happens when these protons start to collide? We know from fundamental physics that when you have two high energy protons collide, they will decay into secondary particles, mostly pions. The pions are unstable. They will decay into gamma rays, muons, which are also unstable, and then ultimately they will decay into electrons, positrons, and several different types of neutrinos. So we started with protons, and we ended up with a plethora of different particles. We know, so now we have these two distinct populations of electrons. One is the primary electrons, which were always there with the protons, and now we have the secondary electrons, which are generated by the proton-proton collision. Now, if we are detecting supernovae in radio from synchrotron emission, and we put in the mix these secondary electrons, we should be able to see them. So that is the whole idea. If we can see them, and if we know how to look for them or what the characteristics will be, we have actually seen the cosmic ray acceleration. There's this little bottleneck there, that the proton-proton collision timescale is extremely large. So if you have a density of, say, 1 particle per centimeter cube, it takes about 35 million years for two protons to collide. So that's not realistic. But if you look at what the typical supernova parameters look like, and if you put in those numbers like a typical radius and the mass loss rate and velocity, the probability of proton-proton collision is not all that unrealistic. It's possible that they will collide. And I want to point out this last equation, which is an interesting one. It tells you what the signature of cosmic ray acceleration will be in these radio observations. So we have these two types of electron distributions. One is the primary electrons and the secondary electrons, which are created from the pion decays. Now, the primary electrons will have distribution going all the way from a Lorentz factor of a few to a million. But the secondary electrons, because they come from pions, they will always be injected at a specific energy. They will not be injected below this energy. The distribution below this energy will be modified by different processes, but they will always be injected at this frequency, at this energy, or larger. And we should be able to see that signature. So that's what we thought, and we did some calculations. Just to show you that it's not completely unrealistic, recently we have discovered supernovae, which are called SuperLuminous supernovae, which are extremely bright, which sit up there way beyond type 1a supernova. And there are several of them which have been discovered. Many people here do research on them. this is another way of showing that they're extremely bright. The point is that some of the theories of superluminous supernovae suggest that they might actually be the emission due to shock CSM interaction, where the CSM is extremely dense, as you would expect. So these are some of the types of objects where you will find realistic parameters for proton-proton collisions. So with that, I will not go through the details of how exactly the calculations proceeded, but I'll give you steps. And if you're interested, we can talk about them, and I'll show you the detailed code. So to calculate the secondary electron, emission from the secondary electron, what we did is we used typical supernova situations where the shock wave is moving as a free expansion into the wind medium, particle injection, which is a power law with exponential cutoff. We consider all different cooling processes which are relevant, like adiabatic cooling, synchrotron cooling, inverse Compton, and how it affects the particle distribution. And then we calculated what the radiation will look like from synchrotron and free absorption. To estimate the PP collision and to propagate them properly all the way, we used the most detailed cross-section that is currently available from Kellner et al. So this is a cross-section that is given. What they do is that they simulate collisions of protons through a code called Sybil, and then estimate what particles are generated, what the distribution looks like, and based on that, they provide semi-empirical formula for what the cross-section will be. So one can take that into account all the way from low energies to high energies and estimate what the particle distribution will look like. This is what the cross-section looks like. And this is what you will see for the secondary particles like electrons, muons, and gamma rays for specific parameters like 1 particle per centimeter cube. Now, what I'm showing here is the distribution of protons in red and the distribution of primary electrons in blue as a function of gamma square and gamma versus the Lorentz factor. You can see that the protons cut off at very high Lorentz factor, and then there are these electron distributions. Every line corresponds to different distance or the evolution of the supernova. So it goes from radius 10 to the power 13 to 10 to the power 17 centimeters. And then, using this proton distribution, we convert them to secondary electrons using the formulation given by Kellner. And this is what it looks like. So again, the red line is the proton distribution, and the blue lines that you see here are the secondary electrons, which are generated from these proton-proton collisions. You will notice one thing, that this secondary electron distribution, it peaks around 100, which is the number I was talking. They peak around 100 because they are generated from pions. They don't go all the way to Lorentz factor of 1 or a few. But then the distribution steepens because of various different processes like cooling and other things. So once we have this distribution, we can calculate what the brightness will look like, synchrotron emission will look like. And this is what it looks like. So I'm plotting a spectrum here, the luminosity on the y-axis and frequency on the x-axis. It should be in hertz, not gigahertz. And plotting spectrum at different times. The red lines are the primary electron distribution, so synchrotron emission from primary electrons that we typically see. The blue lines is the emission from secondary electrons only, and the black is the total. You can see that at early times, like 2 days or 14 days, the blue line is significantly dominant, which means the primary electrons do not contribute so much as the secondary electrons. And so that is the time scale when you want to target the supernovae at appropriate frequencies so that you can see the difference between primary and secondary emission, and you can distinguish it. And so what is that frequency? This is the band, which gives me like a couple weeks to 100 days to carry out these observations. And that's about 10 to the power 11 to 12 hertz, which is not surprising. Which telescope works there? It's the ALMA. So if we use ALMA to observe young supernovae, we should be able to see this. And so this is a light curve at different frequencies. This is light curve at 10 gigahertz, which is where VLA operates. You can see that the blue line, which is the secondary emission, is comparable to the primary emission, so you can't distinguish it if you observe at low frequencies. You need to go to high frequencies. So this is 100 gigahertz, where the difference is significant. And if you go to 1000, which is stretching ALMA a little bit, then the difference is significant at all those time scales. And so this is the current status of young supernovae of the particular type that we would be interested in. What's happening? So I thought we should go back and see if somebody else has observed this effect. Maybe there are observations which exist and we can model them. It turns out that at early times nobody detected these supernovae, but because they were observing at wrong frequency. Wrong in the sense not the frequency that I want to observe at. And so which is why these are all non-detections, which means this is widely open area to investigate. Now the lines here are the secondary emission you would expect for different KEP parameter that Daniel explained. What is the ratio of electrons to protons at a given energy? And if you vary that, you get these different lines, which effectively means that if you do careful observations, you might actually be even able to distinguish between these numbers and estimate what the correct KEP is, which is a big unknown in cosmic ray acceleration field. And so this is the right area to target these supernovae. So with that, 1:28, so I'm on time. I'll give you this take-home message that the first part I didn't speak, but ALMA is in a unique position to observe this secondary electron emission. I'll stop at that. Thank you. Everything was clear? No?
So you're going to be relying on your model prediction for the luminosity of the radio emission to distinguish between primary and secondary, right? Even
Well, that's for the prediction part. When we actually do the observations, it will be the other way around. We'll have the observations and we'll run the models to see what parameters come out of it.
But doesn't the predicted synchrotron emission intensity depend on what you see from the magnetic field, which you do not?
Definitely, it does. So that's a very good question. It gives me a few minutes to talk about what the supernovae do. So the point here is that observe supernovae early in ALMA, but also continue your regular observations at low frequencies. Because at high frequencies, which is ALMA, at early times the emission will be dominated by secondaries. At late times, or at low frequencies, it will be dominated by primaries. So if you have both these observations, you know what is going on, and you can use them to constrain these parameters better. So the conventional observations, which usually happen at low frequencies, you can estimate all these parameters from those observations. If you have that already constrained, you can better model these things.
And you have to follow them for, what was it,
About a year. About a year. Yeah.
How long do your ALMA exposures need to be in order to estimate the spectrum that well?
That's a good question. So if I go back here, so the luminosity is of the order of 10 to the power 25, 26. By the time it comes here, I don't know why is it not moving. But we have checked, if we have to do the ALMA observation, typically it will be something like about 30 minutes to 1 hour, the on source, but calibration can take a long time. So the typical observation, one epoch, will be 2 to 3 hours. To get a sense, because ALMA has comparable sensitivity as VLA, but at extremely high frequencies. So you can get to 50 microjanskis within 10, 20 minutes.